What if I tell you that a single mistake in heat exchanger network design can cost millions in energy loss? But today, you will learn how to solve a threshold problem step by step using Aspen Energy Analyzer and Excel, exactly like real process engineers do in industry. In standard pinch analysis, you need both hot and cold utilities, but in a threshold problem, you only need one. It sounds easier, but it completely changes how you match your streams. Today, we are going to design a heat exchanger network for a threshold problem from scratch. And by the end of this video, you won't just understand it, you will be able to design your own network confidently. Hello everyone, welcome back to Chemical Engineering and Aspen channel. And our today's topic is heat exchanger network design related to the threshold problem. This is not just another Aspen tutorial. In this video, we will combine pinch analysis concepts, threshold problem logic, Aspen energy analyzer simulation, and by the use of Excel sheet into one complete workflow. This is exactly how heat integration is done in real process design projects. So what exactly is a threshold problem? In pinch problem, if we talk about it, we calculate our delta T minimum, or we are given the value of delta T minimum, and this delta T minimum dictates our pinch point, splitting the network into two zones, which is the above pinch and below pinch. As you can see here, that we require both hot utility and cold utility, and there is a pinch point here. This is the hot composite curve, and this is the cold composite curve. However, in threshold problem, there is no pinch point, there is no restriction of delta T minimum. Obviously, we require only one utility, either it could be the hot utility or it could be the cold utility. The system is entirely pinch free. This happens when the heat available in your hot streams is drastically different from the heat required by your cold streams. The trick is knowing how to pair them without violating the value of delta T minimum. Even in threshold problem, which is our today's case, there will be no division of pinch, there will be no rules related to pinch, but there is one rule which is similar to that of pinch, that we should not be violating the value of delta T minimum. The system should be feasible to design. So this is the stream data that has been given to us, that there are 11 streams in the system. If you look at the first 5 streams, the inlet temperature or the initial temperature is higher, while the outlet temperature or final temperature is lower, which dictates that these first 5 streams are the hot streams, and from stream number 6 to 11, the next 6 streams are cold streams in the system. So we will now go to the Aspen energy analyzer, and we will add the data over there. So we will first create the heat integration case over here, and I will first add the nomenclature H1, H2, H3, H4, H5, C1, C2, C3, C4, C5, and C6. Now I have already data in Excel sheet. So what I will do to save the time, I will simply copy it and I will paste it over here. Similarly, I have got the data of heat load, so I will copy paste it over here as well. This step is critical because Aspen is powerful, but engineers don't trust software blindly. If you are skipping Excel, you are not learning engineering, you are just clicking buttons. So after adding up the data, now this is the point where things are gonna get interesting. If we look at this targets view, you can see that the heating load is 0 while the cooling load is present in the system. One utility is now zero in the system. So that means this is our threshold problem. It is not pinch problem anymore. So what we need to do, obviously, for the unsatisfied or insufficient system, we have to specify that utility. Cold is insufficient, so we have to specify the cold utility. And now both hot and cold are sufficient in the system. If we look at the composite curve, you can see there is a wide difference between the hot and cold temperatures, as I have shown you or described in the earlier part of this video. So now we will go to this heat exchange network. Even if you click on this show height pinch line, there will be no deviation, which also reflects that this is a threshold problem. Now, if I take you back to this one, you can see that the stream number 1 has total heat load of 7000 kilowatt. If I sum up the heat load of all the cold streams, it is 4000 kilowatt. As you can see here, the sum is 4000. So even all the heat load of these 6 streams can be satisfied by stream number 1 if there is no delta T minimum violation in the system. There is no process page for this stream set as have been shown. So what we need to do, we need to connect our first exchanger on H1, connect it with C5, double click on it, tied it, and then tying both these temperatures. So delta T at this side is 86, while that here at 86.89 degrees centigrade. Connecting the second exchanger, then tying these three temperatures. So it has increased from 376.9 to 376.8. So it has been decreased. And you can see 116.9 and 216.8 degrees centigrade. Then connecting another exchanger. Similarly, it has decreased from 376.8 to 376.6. 700 kilowatt heat duty between these two, 140.8 and 141.6, way above the delta T minimum. Then connecting the fourth heat exchanger with the fourth stream. Obviously, it's up to you. You can connect any stream in numbering. Similarly, stream number exchanger number 5 in the same fashion, 376.2 to 375.9, 900 kilowatt, 216 and around 306 degree centigrade is the delta T on both sides. Connecting the last heat exchanger, process heat exchanger actually, and 22 130. So it has gone from 375.9. There will be slight difference, and the heat duty here is 200 kilowatt, while the delta T here is 246, and here it is approximately 356. Now you can see all the cold streams are completed in the system, or in other words, they have exchanged heat. Now, any hot stream cannot exchange heat with any cold stream. Obviously, for this, we need to now introduce the utility in the system. And as I have told you, if you take you back to the Excel sheet, that its heat load will be remaining as 3000 kilowatt, while the 2, 3, 4, 5, these will now exchange heat with the utility. So what we need to do, we need to now connect this with the utility and tying it. It has been satisfied. Tying the second one here with the stream number 2, which was not utilized, and it is tied. Available results. Again doing it, tying it, results available, calculations okay. Then again with stream number 4, whose number is H5, and in the same way doing for the last one, and you can see it has been tied as well, and our network is now completed. So you can see that with H1 we have successfully heat exchanged with all cold streams, and then remaining H1, H2, H4, H5 and H3, they have been transferring their heat to the cold utility, the cooling water, which is obviously coming from the cooling tower. If we look at the targets, these are the targets available. If we look at the design, 100%, so this has been the optimized design till now, which we have done. Obviously, you can change the scheme. Instead of H1, you can connect H2, H4, H5, H3 to see whether you can achieve the more reliable or more optimized design or not. In real plants, heat exchangers account for major energy savings. Poor design increasing capex, which is the capital expenditures, and opex, operational expenditures, significantly. That's why tools like Aspen are widely used in industry. If you understood this video, you now know more than most students about heat integration. In the next video, I will show you pinch-based network design for non-threshold problems. Like this video if you want more Aspen tutorials. Comments HEN if you want advanced problems, and subscribe because we are turning theory into real engineering skills. Till then, it's goodbye. Stay tuned for more exciting updates and lectures on this channel.